First things first, today's lab is going to be not the lab activity in the book for the simple reason of because we moved the exam, we're 3 lectures short of where we should have been for doing this lab. So we haven't talked about the optics of how a lens works. So instead, I gave you a little worksheet that we will periodically pause for you and the people at your table to work together to solve the different problems as we get to them. And so, like Michael, you'll want to or somebody else unless you want to work by yourself, and likewise, Lydia. I mean, if you guys want to work separately, you're free to. I do not want any groups of over 3, so either you 2 join together or one joins that group and the other one works alone. So I would recommend working together. Okay, that said, there is another thing. I was talking to Dr. Wolf over the weekend, and we were, thinking back about, why are students in general physics? And, well, I usually take it because they're most likely pre-med or pre-det. How many people is that not applying to? Not applying? Wow, that's a pretty good number, actually. So, maybe my ideas weren't so hot then. But why is it required for pre-med and pre-det people to take this class?
Critical thinking.
Critical thinking, because they want you to develop the skills of, instead of just being told, here's the numbers, put them into this equation, to have to figure out what's applying here, what's actually going on. And so a lot of what we've been doing has been working toward that end. And as Carrie and I were talking about this, I was like, maybe the students would realize the applicability more if I actually put some questions on the test that come directly from MCAT questions. And Carrie said, probably you should ask them if you want them to do that, or if they want you to do that before you do it. And I see Mira already says no. Trey says no. Absolutely not.
I don't care.
What would the others think? What?
Do you think that those are a different level of difficulty?
No. I actually looked at some beforehand and I was like, wow, that's just like what we do. I just have to put the preface MCAT question. That's the only way you know it was different.
Yeah. I mean, we're equipped for it.
Yeah, I'm like,
yeah, you're definitely equipped for it.
Would it be an application then? Is that where they would kind of
they would either be knowledge or application.
Yeah.
Messing.
This is something I wish that all of my science teachers would incorporate into the curriculum and all of our tests, so I think we should do it. Because it's really important for us to prepare for these MCATs and DATs, or else we get left behind by all the schools that have them doing it.
Yeah. Well, I've always prided myself. I actually did an analysis once of students who took physics from me and students who took it elsewhere, because ever since I was in college, that's been the trend. People take somewhere else where it's simpler. And on the 1 to 15 scale, people scored 1 point higher in physical science compared to their other scores if they take physics from me compared to if they took it off campus. So I felt really good about that I'm preparing students for the MCAT well. You have a question?
Yeah, well, I was just going to say I agree that they should be, as long as we're, like you said, prepared for it.
Yeah.
wait, are you talking about putting it on a test? Or
Yeah.
just...
Yeah, on test.
Okay.
So I will put a few on, I'll mark them. So if people are like, or they,
And if you're not pre-med, you don't have to answer.
Yeah. I was like,
Is there extra credit?
can you do that?
No.
Please.
I took
No.
biochem, and he was doing that on our test, and I honestly didn't even realize it until he said something.
Yeah, because the questions are based on what you should be learning in this class.
Yeah.
So it's the same level of difficulty?
Yeah,
Okay.
it's and the questions on the MCAT are not ones that require heavy thought. They're just ones that we require the basic knowledge we've been learning.
Okay.
For the most part. The hard part, well, there's just so much on the MCAT, right? And it's not easy subject matter. And they made it so much longer too. They want to give you more time per question. And you have like a fraction of a second more per question now, but you have a lot more questions too. Isn't that nice though? Anyway, so I will do that. I will mark them so you know which ones are ones that came from MCATs. And I was looking at different MCAT questions. There are some that has like a big paragraph and then like 10 questions on it. Those would be more like our synthesis questions, but obviously I can't put all of that on your test. And then others were just like, simple applications, a one-stepper. So I will, of course, try to be judicious in my choices. All right, let's get on to the material for today. I gave out all of my, I can't believe I did that. I gave out here's one. Whew. Everyone has one of these, right? Yeah. I just want to make sure that I stop at the appropriate places. So we're going to be studying geometric optics now, right? We transition from electromagnetism into optics. And when we talk about geometric optics, that's not all of optics, but it's applying geometry principles to solving optics problems. So you know that one of the prerequisite for this class is college algebra, which really is minimal. Some schools will require you to take trigonometry before you take this class. And I think you could all acknowledge at this point that would help. And this is a place where you're going to be using geometry and trig stuff a little more than we have in the past. So the geometric optics works if you have the sizes of optics and openings. It's much bigger than the wavelength of light. Shocker, what's the wavelength for visible light from yesterday's lecture? Okay, from 400 nanometers to 750 nanometers. A nanometer meaning a billionth of a meter. So we're talking less than a millionth of a meter for the wavelengths. So as long as our openings are much larger than a millionth of a meter, they're always going to be, right? Then it's applicable. We also talk about this as ray optics. I usually get a laser out and point it around the room at this point. Light behaves like a ray. A ray has a starting point but no ending point. Light will have no ending point unless it hits something. And it just travels in a straight line. So we're going to draw straight lines for the paths that light takes unless it hits something. So with that in mind, a review question from last class period. Good. How is the angle of reflection measured? Measured from where to where?
C.
Okay, it's still C because I didn't even change the order of the answers. It's the angle between the normal to the surface and the reflected ray. It's important to remember that, especially because today we're going to be talking about a new thing, refraction. Refraction is light bending when it goes from one material to another. And you might have noticed this. Let's say that we had Ryan, the swimmer. No, I don't know. I'm trying to remember from his scrapbook entry. I think you're talking about, was it you they said looks like
My brother.
Oh, your brother, okay.
Yeah.
Trying to remember, it's been a while anyway. So let's say we see Ryan standing in the water. And so if you're standing over here and Ryan's standing in the swimming pool, and you look at him, what does his body look like?
Sorry.
Maybe we shouldn't have gone there. If you have a rod sticking up in the swimming pool, and you look at the rod, what does it look like?
Oh, like.
It looks like it bends when it goes into the water. And of course, as a little kid, you, like me, may have been a little confused as to what's going on and had to go inspect, like, this thing looks like it's bent. I go over and check it out. It's not bent. What in the world's going on? It's not that the object is bent. It's that the light bends. And our brains say, light travels in a straight path, and so without having real intimate knowledge, we just assume that we're looking straight, and it's actually going like that. So what's down here we see is out there, and that's why things look bent. So let's get into that a little. Pass on that one. I talked about this. I didn't show any math equations. Let's just show the math equations here real quick. Mostly because it's kind of a trig problem. I have two triangles here. One that has, I've changed it black here. One that has the red line, the black line, and a blue line. One that has the blue line, black line, I guess let's call it cyan. Those two triangles share the same side, so those are the same side. And we know that due to the law of reflections, these two angles are the same. So we have a size the same, the angle is the same. And this angle here is 90 degrees. So that gives us something that we would call in my high school geometry class, angle side angle. Do anybody remember that?
Yeah.
Angle side angle means that the two triangles are similar triangles. Or identical triangles. I don't know. And so that means I should be able to make ratios between the sides. So in this case, I'm just going to compare the blue side to the red side. Those should be the same length because, well, yeah, it's got to be their identical triangles. So if the blue side and the red side are the same because the triangles are the same, then if this distance here is the distance, I'll call it HE for the height to the eyes, then each one of those is 1/2 of the height to the eyes. And so the bottom of the mirror needs to go halfway between the height of her eyes and her foot. And then you have the same exact thing going on for looking at the top of her head. So that, I think it's pretty clear when I draw out the triangles to see that you need half of the height in mirror of the person who's looking in to see their entire body. And then the last thing I mentioned in class is where you hang it is important. And I think Ryan's probably with me here. It's really annoying when you go like to the hotel and you want to do something like shade. A basic thing in shade is you want to see your face. But no, they have the mirror this high. The mirror is this high and I want to see my chin. Well, it never works out and I have to do things like go like this. Right? Because they don't hang them high enough for me. They hang them high enough for most people, but you have to have it going above your eye level if you're going to see the top of your hair. And, see my chin, it's going to have to be at least this high for me to see my chin. So I just wanted to give that another little talk. One of your homework questions is essentially like this. We have light coming in, reflecting off of the surface. This has marked theta 1 and theta 2. What should the relationship be between theta 1 and theta 2? It's actually simpler than both of those terms. They should be equal. Theta 1, I said the question wrong.
Theta 2 and theta 2?
Between theta 1 and theta 1, or theta 2 and theta 2 is what I meant to say. I was thinking that these were labeled 1 and 2. Angle of incident is equal to angle of reflection, right?
Yes.
So if we take this and we say, how much did this light deviate? So here's going straight, and here's the deviation. How much is deviation 1? Not necessarily.
90 minus theta?
Okay, so we have one answer, 90 minus theta. 90 minus theta is the angle there. But I want the total deviation from going straight.
Oh, maybe theta plus theta.
So it would be,
Oh, no, wait. Sorry. 180 minus theta plus theta.
yes, 180 minus 2 theta, which is just double what he said the first time because you cut the angle in half. So the deviation 1 is going to be 180 degrees minus 2 theta 1. By the way, you should probably be riding along because this is the first problem and you can't just have the answer. You have to have your work. Oh, no. Oh, okay, things got way out of hand. This was supposed to be the first problem, but when I pushed them in, apparently I got them out of order. So yes, it's number 3, my mistake. Wow. So deviation 1, and I'm going to erase that. So deviation 1 is 180 degrees minus 2 theta 1. Now your problem says, so I'm going to call this alpha. Alpha is the angle between the two mirrors. In this diagram, alpha was 90 degrees. But in your problem, alpha is not 90 degrees. In your problem, what is alpha? 80 degrees. So we're not going to get the nice simple situation, which actually would have matched words that were coming out of Ryan's mouth earlier when I misspoke on my question. But since we're using a different angle than the 90, it's going to be different. So if this angle is alpha, how could I find what theta 2 is? There's a different way. Depends on your love and joy of trigonometry, how you want to do it.
Well, we know that the angles are equal to 180 in a triangle.
Okay, the sum of the interior angles of a triangle is 180 degrees.
So then we can just subtract out theta 1 and 180 and we get that side. If we solve for that top corner right
Okay,
there, would that give us-
so I think that what he is doing is going like this. Is that right?
Say yes,
Yeah, kind of.
he's like, that's a
Okay.
Yeah.
Kinda, he says. Kinda, maybe, a little. Okay, let's suppose this is one of the two common ways of doing it. So it's one of the ways. The other way is, of course, just to work with the triangle that has alpha in it.
That one's more straightforward than what I was thinking.
They're equal. Okay, so let's do that. We know this angle is theta 1. This angle is theta 2. We could find this angle, and we could find what theta 2 is, right? So how big is this angle? It's actually not alpha. At least I don't think it is. Remember, these are surface normals. So we know those two angles are 90. What's the sum of the interior angles for a four-sided shape? 360. So we know that 360 degrees is equal to 90 degrees plus alpha plus 90 degrees plus beta. And so we can solve that for beta. Beta is equal to 360 minus 9 minus 90 is 180. 180 degrees minus alpha. So it is the complement to alpha. Right? Or is it supplement? Supplement to alpha. Been a long time since we used those words. Yes?
Well, if there's some kind of rule that says, like, I mean, with two 90-degree angles, right, that's what the green lines?
Yes.
Doesn't that mean that other two have to be 90 degrees? Like, how can
No, it means they have to add up to 90 degrees.
the other two? I mean, no.
Then you have to add it to 180.
Or, yeah, up to 180.
Right. But how do you have two 90-degree angles when these are also less than or greater than 90 degrees? Are we not defining that as a rectangle?
No, it's not a rectangle.
Okay.
It's a four-sided object.
Rhombus or something?
But this, the mirror is not.
I'm sorry.
I'm not good at making the shapes with my fingers, but yeah, it's
Is it a parallelogram?
it's actually not a parallelogram because the sides aren't parallel. Parallelograms have to have parallel sides, and this doesn't. But it has two 90-degree angles, and with these two 90-degree angles, I could do something like put them like this, right? It doesn't have to be all four 90s. So beta is 180 degrees minus alpha. And once I have beta, then I can go back to the rule that DJ gave us and find what theta 2 is. What was your question?
So why again is it 180? Is it because you have those two 90-degree angles?
Yeah, 360 degrees has to be the sum of the interior angles. And so these are the four interior angles on that shape. So now that I have beta in terms of alpha, now I can find theta 2. I have a triangle there that says theta 1 plus theta 2 plus beta equals 180 degrees. Substitute in the beta, and I will have theta 1 plus theta 2 plus 180 degrees minus alpha equals 180 degrees. And what we find, lo and behold, is that theta 1 plus theta 2 is equal to alpha. So theta 2 is equal to alpha minus theta 1. So there I have theta 2. How big is the deviation here? The deviation at the top there, delta 2. That is a funny delta there, by the way. There's more than one way to write a lowercase delta.
That would be 90 minus theta 2. Theta 1. Oh, wait, no, because it's going through it. So it'd be the same as last time. It'd be 90
Yes.
minus 2 theta 2.
So now we're going to have delta 2 is equal to 180 degrees minus 2 theta 2. Put that in terms of theta 1. Actually, I don't want to. I'm petulant. What's my total deviation? That's what we were asked for. So my total deviation is 180 degrees minus 2 theta 1 plus 180 degrees minus 2 theta 2, or 360 degrees minus 2 parenthesis theta 1 plus theta 2. And the reason I was petulant is I realized at the last moment I already have theta 1 plus theta 2 as alpha. So this is doing geometric optics to find what the deviation of the path is. So 360 degrees minus 2 alpha. You obviously have alpha is 80. You can do that work. What would it be if alpha was 90 degrees? It'd be 180 degrees. It'd be 360 degrees minus 180 is equal to 180. We call that situation a corner cube reflector or a retroreflector because the light that comes in will always be reflected straight out. It doesn't matter. Notice it doesn't matter what theta 1 was to our answer. It's going to be deviated by the same amount. So, for instance, on the moon, they put a big old retroreflector so they can shine a laser beam from the Earth, hit the moon, and have it bounce straight back to them, and measure the time of flight for the laser beam to go up to the moon and back. Or so I'm told. I've never verified it. So, is this useful? You bet. Where do you see these all the stinking time? That is the retroreflector, the corner cube reflector. If you make it three-dimensional, so you cut off a cube, then it doesn't matter. Right, this here was only two-dimensional. Where on a bike, then we'd be more specific, because yes, you see it on a bike a lot.
On the bike side, the light shines on someone's bike, and it'll shine back. They don't hit them.
The reflectors you see on a bicycle are made with just, it's a bunch of glass that's made into corner cube, a whole bunch of those little corner cubes. So light that comes in, hits that glass, reflects straight back. So if a car is coming at the bicycle from this direction, it will reflect straight back to the car. It doesn't reflect over here like the law of reflections would have said if we put a pointed mirror there. Right.
What about construction worker bill?
Yes, same idea. I don't know how they do that construction because it's little tiny things, but
How do you, so we're talking about the deviation
Yeah.
angle, is that just, how do we know exactly what?
so the deviation is take the angle from straight to where it actually went. So see, I drew straights on each one of those. It's a good question. The first time or two going through this, I wasn't sure how to define the deviation either. Yeah, because the problem just asked what's the total deviation. I'm all, well, the angle between this and this. Go to each one and measure the deviation for each one and add them up.
So,
Yeah.
the deviation angle is the sum of all the deviation angles?
Yeah, the sum of all the deviations. Yeah. Because it bent by delta 1 at the first one, then bent by delta 2 at the second one. So the total amount that it bent was delta 1 plus delta 2. Okay, because this is part of, same skills you have to have for a homework assignment problem that's due tomorrow. Are there any questions on this?
How did you get the theta 1 plus theta 2 is equal to theta A?
Yeah, glad you asked. Magic. That was the result, actually, of when we did the triangle here. This triangle right here. We had theta 1 plus theta 2 plus beta is 180 degrees. Substitute in for beta. So beta was 180 degrees minus alpha. And that's how I got this.
Okay.
I just wanted to say it was magic. That's why I said glad you asked. Now, something that goes without saying, I mentioned this before, all light is transmitted or reflected or absorbed. And if you look at something like a window, like we have a window up there, we tend to think that all the light is coming right through. But about 4% of the light is being reflected. So in fact, if I take a bright light and I shine on there, you would see it reflected back in the classroom with about 4% of the original intensity. We'll talk about one-way mirrors later, or one-way, two-way, mirrors where you can see through one way and not the other. Those are something where you have changed that reflectivity to be something closer to around 50%. But we'll talk about it later. It's not a subject for today because we want to get to other things for the lab. Yeah.
Sorry, going back to the other one. If we're adding up angles, does it matter which way they're going? Like maybe subtracted. Like if we're looking at the total way that light was refracted, would it be destructive and constructive?
Okay, this is reflected. Refracted is a word for today, but this is not it.
Okay.
So it's important to get those separated in your mind because they're so similar.
Yeah.
So
like if light was going this way,
Yeah.
and the angle kind of went this way,
mhm.
and then it was going that way, and the angle kind of went like,
Yeah,
would those be subtracting from?
right, because one's a positive angle, one's a negative. You have to decide what direction you're going to consider positive and be consistent.
What's the standard?
The standard is that counterclockwise is positive.
Okay.
But you can decide, right?
Yeah.
Always you can decide. Okay, index of refraction. So here we have that word refraction. Index of refraction. An index is something that tells you about. So this is going to be something that tells us about refraction. Refraction is the name for light bending when it goes from one material into another. And the first question is, why should light bend when it goes from one material into another material? The answer to that is because light travels at different speeds in different materials. People often get confused and say, light travels at the speed of light. Duh! Light in vacuum travels at the speed of light in vacuum. Light in glass travels at the speed of light in glass, and the two values are different. And so the index of refraction is actually a number that tells us how fast light travels through a given material. So I have up here the table from the textbook of indices of refraction. Remember, the plural of index is indice. Indices of refraction for different materials. And the definition of the index of refraction. So here is the definition for the index of refraction. C. What did C stand for? Speed of light in vacuum. Remember, it's important that we designate the material because we're going to be comparing V, the speed of light in the medium's whatever material I'm interested in, to the speed of light in vacuum. Oh, I'm sure I have the wrong number of somethings there. Vacuum, 1C, is that right? So the index refracts the speed of light in vacuum divided by the speed of light in whatever material you have. One of the fundamental rules in physics is that nothing can go faster than the speed of light in vacuum. Not even light can. So in other vacuum, it's slower. So light going through air is going slower than the speed of light in vacuum. Light going through glass is going slower. Light going through diamond is slower. So before I go further, I do need to specify once again the value for the speed of light in vacuum. 299792458 meters per second. Exactly. Now, for our purposes, probably 3 significant digits is going to work. If you go to a 4th digit, it's going to be 2.998. So that's why I stopped it at 3. So now we have questions like, how fast does light travel through, let's take water. How light does light travel through water? Go ahead, say louder.
No, I don't want to say.
Come to count on you to say what you're thinking, Ryan.
All right, 33% of that speed. That's what I said.
Okay, 33% of that speed. It's actually 66. I think 60.
I was on the right track.
Yes, you were on the right track. Because we take this equation, notice if n is c over v, then v must be equal to c over n. And so that would be 2.99, well, okay, we're going to go easy now. 3.00 times 10 to the 8 meters per second divided by 1.333. Between friends, that's 4/3. And so divide that by 4/3. And so 3 divided by 4/3 is equal to 9.00 times 10 to the 8 meters per second. Okay, it wasn't 66% either. I was wrong. Divided by 4. 9 divided by 4 is 2.25. So finding the speed of light in a material is very simple if you know the index of refraction. Now, for your, this is number 1. I gave you way too much space for solving this. What's the speed of light in diamond? So go ahead and work it out now. If you've already done it, okay. I think so. All you have to do is that. There are other ways of doing it, right? You could have just used this triangle here and yeah.
Are we at 20 degrees Celsius?
Right. That's the other primary way to do it.
We're gonna assume that is
Looks like a big white spider. It's an albino.
That's why it's just this one. That's how you figure out what things you decide. So,
They wouldn't get her right. This was 90 degrees. Then I chose 90. That's why I chose it to not be 90 degrees. Because this way you have to actually. Yes. So are we all good? The difference between zircon and cubic zirconium? I don't know. Probably isn't any. All right. Somebody who feels comfortable enough to blurt out how they did this.
So like same thing but a different number for n.
Yeah.
Okay.
I did the same process. Whoa. Ooh, that would have minus that one day.
Okay, so what's the different number?
The different number is 2.41.
Units for index refraction, it's unitless. So if we divide those out, I should get 4 significant digits to my answer, right?
So I used 3 instead of that big number, 3 times 10 to the.
Mm-hmm. So your answer is going to be probably off in that last digit, right?
Yeah. Yeah, mine is 1.240.
Okay, that wasn't hard, right? This is part of what makes diamond special for rings. Because the light goes really slow in there, then it does things a little differently than if it went faster. And so that differently thing is called refraction, what we're going to get to soon. Now there's another equation that I have here. And usually I go through a lot of rigmarole on this, but here's a basic rule. When light or any wave goes from medium 1 to medium 2, the frequency can't change. The frequency has to stay the same. This is true for all waves. When we get to some of the discrepancies between the wave theory and the particle theory, this is going to come back. So the frequency for a wave cannot change when it goes from one material to another. But as we just saw, the wavelength, the speed does change. And because there is a fixed relationship between the wavelength, the frequency, and the speed, if the frequency stays the same and the speed gets slower, then the wavelength is going to have to get shorter because it's going a smaller distance in the time for one cycle. And so using our index of refraction equation and solving V equals C over N, wavelength is V over frequency. Replace that with C over N. While C over F is the wavelength in vacuum, which I called wavelength sub 0. And so the wavelength in some medium is going to be the wavelength that you have in vacuum divided by the index of refraction. So for instance, in diamond, the wavelength is less than half of what it is in air. Now this comes back to something kind of interesting. I talked about light, and I am so comfortable talking about light and wavelengths. 400 nanometers to 750 nanometers. That's the wavelengths of light in the visible spectrum in vacuum. If we have that light going through water, the color blue has a different wavelength because the slower speed makes it so there's a shorter wavelength for blue. So instead of 400 nanometers, it's going to be, let's say 350 nanometers. But the frequency stays the same. If I could go back and start at your level and change the whole world, we would just talk about the frequencies of light, and then it would be more consistent. The frequency doesn't change when it goes from air to water. But I'd have to change all the physics books and everything to make that happen. I've got that kind of energy. But it's important. The wavelength changes. Why is that important? Well, remember Huygens' principle. Christian Huygens, his last name, Huygen, is pronounced Huygens. He said that every point on a wave front can be treated as a point source for new light. So if I have light traveling through something like air here, the light travels, and here's a wavefront. Remember, the wavefront is where we have peaks on our waves. And I can treat it like I have a whole bunch of little point sources, a whole bunch of light bulbs here, and what's the light that they're going to give off. And I can use that to check how light propagates. And when I say it, I think it doesn't really resonate with many people. It resonates much more if we see how it works. So I'm going to go to, let's try that again. I'm going to go to this website here, which I already have queued up. So this website is, I think, a wonderful place to understand what Huygens principle actually comes out to be. So it starts out just showing a plane wave. So this is a wavefront coming down. Now this first one, I think I'm still, nope, it's not the first one. This is the third one. Got to restart. I wanted to start with the second one actually. So this here is going to show that plane wave coming down, and when it hits the medium, each of the little points is going to be a point source as per Huygens, and you see that then light is being produced from these and spreading out. Well, if you look at that, you see that we now have light that's going out, and if you add those up, well, I'll go to the next step because it adds them up for you. Well, I think I went to the third one. I wish it told me which one I was on so I would know for sure. Yep. So here it's adding them up, and you see the red line, the blue line is adding up all of them that you get from Huygens principle. And so what you get is a new wavefront that's traveling, but notice the directions they're changed. The upper one, it's a reflection. That's going to be following our law of reflection that we already saw. The lower one is a refraction. You notice this is not parallel to the black line. It's bent. We call that refraction, the bending of light. And so the direction the light is actually traveling is going to be normal to that. So the light is traveling, oops, wrong tool. The light is traveling like this. So it's perpendicular to the wavefront. So the direction the light is traveling has now shifted. And so one of our fundamental goals for right now is to calculate how much the light has deviated from going straight. How much did it bend? And so to do that, we just take some simple geometry. So here's showing one wavefront separated by one wavelength in air, and then the next wavefront here separated by one wavelength in the glass in this case. And if we look at triangles, we have here, that's the same for both the triangle above it and below it. And this has the wavelength in air, and then a right angle to this that nobody actually cares about. This one has the wavelength in the glass. And so we want to relate the angle of incidence with the angle of transmission, right? Now, those angles might confuse you. Those angles are between the wavefront and the surface. That's not the angle of incidence or angle of reflection type measurement. What was the angle of incidence measured from? Normal to?
Surface.
Okay. It's the angle between the normal to the surface and the incident ray. Here, the thing that's marked theta I that I have looked at is between the surface and the wavefront. But keep in mind, the wavefront is 90 degrees from the direction of propagation. So the incident ray is 90 degrees from the wavefront, and the normal is 90 degrees from the surface. So it turns out that this angle here, marked theta I, is the same as this angle here, marked theta I. And likewise, this angle here marked theta t between the wavefront and the transmitted ray is 90 degrees from this. So this theta t is the same as that theta t. So even though my picture doesn't have this ray and this ray, it's still relating this to this. And so if I look at these, I would have taken the upper triangle. So I'm just cutting out the lower stuff on my screen so we only see the upper triangle and erasing stuff that's getting in the way. I want to compare this distance h and y initial, or y initial. And so for the triangle, the y incident is opposite side, and the h is hypotenuse. So that means opposite and hypotenuse, those are related by sine. So sine of theta incident is equal to wavelength incident over h, which in this case actually stands for hypotenuse. So that's what I have for the incident side. Now looking at the transmitted side, I have again the opposite side and the hypotenuse. So sine of theta transmitted is equal to the opposite wavelength transmitted over hypotenuse h. So I have these two triangle relations, and then I just take those two and I divide them by each other. So I just take sine of theta incident over sine of theta transmitted is equal to wavelength incident over h divided by wavelength transmitted over h. The h's cancel. And so I have that relationship. Now I'm simply going to go back to what we had on the previous page that said wavelength is equal to wavelength 0 over index of refraction. So using that substitution, wavelength in vacuum divided by n incident divided by wavelength in vacuum over n transmitted. Well, now the wavelengths are going to cancel. And I'm left with sine theta incident over sine theta transmitted is equal to n transmitted over n incident. Now, some people I might have just lost. I had over here 1 over n incident and 1 over n transmitted. But when you have dividing fractions, you take the bottom one, invert it, and multiply. So I have 1 over n incident times n transmitted over 1. That's where I got n transmitted over n incident. This is Snell's law, but we usually cross multiply. So if I cross multiply, I have n1 sine theta, or n incident sine theta incident is equal to n transmitted sine theta transmitted. If you look at this equation, it actually will remind you of something that you noticed with the law of reflections. I have incident on the left side and transmitted on the right side, but the left side and the right side look exactly the same. What's the net result of this? Light behaves the same going forward and backward. Light going from me to the window is going to behave exactly the same as light going from the window to me. We put a lens in between, it's going to do the same thing. So light going forward and backward is going to behave the same. So it doesn't matter which side's incident, which side's transmitted. Hence, very often, we just put n1 sine theta 1 is equal to n2 sine theta 2. And we don't specify that one's the transmitted and one's the incident because it doesn't matter which one's which. But there are things that matter here. If you go into a material that has, let's say, n transmitted, missed. Let's say n transmitted is a bigger value than n incident. Let's start with the simple question. What does it mean if n transmitted is bigger than n incident? What does that mean? If N transmitted is a bigger number than N incident. What do the N's tell us?
The amount that it's going to.
Okay, it's the speed of it which is what dictates how much it's going to refract. So you were thinking right in both cases. But it's directly telling us the speed. If N is bigger, what's that telling us about the speed?
It's going to be slower.
Slower. So if N transmitted is bigger, it's going into a slower medium where light travels slower. But if N transmitted is bigger than N incident, then what does sine theta transmitted have to be? Bigger or smaller? Smaller. So sine, a smaller angle gives you a smaller sine theta. So if you have N transmitted is bigger than N incident, then theta transmitted is going to have to be smaller than theta incident. So this gives us an important rule. When light goes into something that has a slower speed or a larger index refraction, it will bend toward the normal. So in this figure, because glass has a slower speed than air, the light deviated toward the normal because it was going to something slower. Now, if I reverse the light, it would be going from a slower speed to a faster speed. Then what happens? It's going to go away from the normal. So if light comes out here, instead of going straight like that, it deviates away from the normal. So when you go into a faster medium, light deviates away from normal. Slower medium, it deviates toward the normal. Let's look at some practical, actually seeing stuff. These two. And this one.
Is this from the worksheet?
We have a problem that we have to do right as soon as I'm done with this. So, yes, kind of. So back to this here. I have light. I used mirrors yesterday. Today I'm going to use pieces of plexiglass. So I'm going to have this light go into the plexiglass. And notice that the waves, they didn't go straight. Which way did they bend? Did they bend toward the normal or away from the normal? Toward. Now, to make sure we're clear, normal is the surface normal, so the normal is pointing like this. They bent down, so they bent toward the normal. What about when they came out? They bent away. So I can bend this more, change the angles, and I get more bending as I change the angle here. So what we're seeing is a practical application of this refraction, light bending, because it's going from a material with one speed to a material with another speed. So now we have problem 2, which of course should have been 3, which says if the angle of incidence is 30 degrees and light is going from air into diamond, now what's the index of refraction of air?
1.
If we look at this table, it's not exactly 1, but we'll treat it as 1. Air is 1.000293. Between you and me, that's 1. And so we're going to have theta, or N1 is 1.00, and N2, or you can put a third 0, 1.000, and N2 is 2.419. Yeah.
Are there any gases that we would just assume it's 1? Or
Yeah.
treat as 1?
Sure. I'm trying to think of, right, because all of those gases are, but if you raise the pressure, then it's going to become a slower speed. I can't name anything offhand, but if you get a dense gas, it's going to be something you probably won't consider 1. And in fact, it makes a difference. I was talking to somebody who is on the gymnastics team, and of course they're driving to California over break. And I say, oh, well, you might see mirages as you're going through the wasteland known as
Death Valley.
Western Utah.
Oh, yeah, true.
Right, the Bonneville salt flats are out there. It is just flat. And you often see nice mirages. A mirage occurs, like we'll talk about it. It was in the lecture stuff today, but I took it out because we want to focus on the eye. The mirage occurs because the index of refraction is slightly different in hotter air than it is in colder air. And so light is refracting because of that change in index of refraction, so that when you look down at the ground, you actually are seeing a pathway up into the sky. Okay, so everybody working on, I should go back to the slide of the day. If theta incident was 30 degrees, I think, and if you start in air and you end up in diamond, what's the theta transmitted? Yes, there you go.
That's the same thing as the angle of refraction. It's transmission, the same thing as refraction.
Use the formula this time. That's a good shot.
So what's the
I'd rather hear from that than
So we're saying that they would go into the
guys, when is it like?
Yes.
What is going on?
Yes. There's a question.
reflective is this one?
You doing a lot of studying? Okay. Are you doing a lot of studying?
No.
Is it what?
Reflection was the rule for
I'll speak up. That's
Hey,
exciting.
scoot closer.
I'm really switching. And then everything. I actually changed.
Oh, so then makes sense. He does all of his own.
That's not true.
Is it good?
You want to find this important.
Everything's good.
So this battery. What?
Yeah.
But everything's
Wait,
that's actually fast. I feel it.
so is anything related to school?
Did that. This equation is definitely.
Yeah.
No, actually, what?
Andrew, is anything related to school or just something like recovered life stuff from?
School, right? What's that?
I don't really like when you do like this.
This side here should be connected that way.
Oh, it's the same, right? Yeah.
Yes, I prefer.
Well, oh yeah, it is. I think it's the same.
Trust me. That's the one question. No, it's pretty much general. Let's come back to 1/2 divided by 2.0.
Have you started?
We only get one angle. It's not even right.
Not really. I have to look back at that video she posted because I
We're
never.
trying to get this. Like I've done the whole
We have
primary
two.
or supplementary.
We did one.
I even did the whole like.
I
two
am
months
not
people
even
do that.
joking you.
Right?
I am going to get one
But
of my
then like
grades.
I don't know which one.
I think I'm gonna do okay.
Because we're not equivalent.
Well, we still have 6 tests.
Oh,
So I know that people.
literally that's
You just have to.
And none of them are like the same one too.
Yeah, you don't pay support because.
I'm so much
Yeah.
better.
You just do
Right. I don't.
two sides.
I thought it was straight shot.
I thought it was Wednesday
Thursday
yesterday.
have to just.
I just don't know how much it is.
No, that's what I was like, that's what was putting down right now.
You did the equations?
But this one?
It goes. Did
In
you get his back?
In I sine theta I in T sine theta.
Yeah, I figured.
Your one is looking a little
Okay,
dark.
so you know what sine theta I is?
Oh, sine theta I.
Only it's.
Uh-oh, battery is running low. Nathan?
Oh, 30 degrees. Oh, so this was 30
You have to get under the desk there and unplug the.
Angle
So it's.
Yeah, so I get like 30 degrees.
What's it look like? What's that? It's it goes into here. So sitting on top of my desk is that, and then trace it back. Battery runs low. Okay. So there were two questions on this. Let's start with the easy one. What is the angle of reflection? So here's the picture. So the angle of reflection is the same. So if this was 30 degrees, then this should be 30 degrees. Then it said the angle of refraction. What does refraction mean? Bending when it goes from one material to another. The angle of refraction is the one that's labeled here as the theta transmitted. And so it's not like theta transmitted and theta refracted are two different things. Because it was transmitted into a new material, it was refracted. And so I think we all agree. What should that angle have been?
9.93.
Okay, 11.93 degrees. I do. And of course, I didn't calculate that, but it looked like everybody was getting the same thing, which generally means it's correct. The premise behind the TV show Wisdom of the Craft. Or the premise behind their, what? Family Feud? Well, no. But there's like a website that has amateur people look at galaxies and determine what kind of galaxies they are. And people come in with no knowledge, doesn't matter. The average turns out to be dead on. All right. Now to thin lenses. Thin lenses, because correction of vision, remember today's lab is about the eye, is done with thin lenses. First thing is when we're talking about lenses, we're going to talk about the principal axis, which is the axis that goes through the center of the lens. So I have a lens here. The principal axis is the axis that goes through the center right there. That's important. All of our work is also going to be done with what we call paraxial rays. What does paraxial mean? It means parallel axis. Paraxial rays are rays that are very close to parallel to that principal axis. Thank you. You guys these too. Apparently I've been teaching too hard today. Killing my battery. Everybody remembers why I say battery. So we're going to deal with paraxial rays. Rays that are close to parallel. In our diagrams, they won't look close to parallel, but our geometry requires that they're close to parallel. And so we have things that we call aberrations. Aberrations are errors in the images. And the aberrations, one of the aberrations will be an off-axis aberration. If we're not dealing with paraxial rays, then we're going to have an image that's different than what we calculate. Refraction, bending of light, can be used to bend light differently if you change the angles. So we have here two types of lenses that are made. It's broken up into little pieces just to illustrate that you have light bending on one surface and bending on the second surface. So I will use this as an example of that simple lens idea. So here light comes in, it bends on the front surface, it bends on the back surface. One thing that you'll note is the bending is at two different locations. The thin lens approximation, where everything said thin lens, is going to be that the lens is so thin that all the bending can be treated as if it occurs at one point in the center. So that's another thing when we do thin lens calculations, we're assuming a very thin lens. If the lens is thicker, then we're going to have some aberrations again. So let's just make some lenses. Here is a lens that's curved outward on both sides. If it's curved outwards, we call it convex. So this is a double convex or biconvex lens, or convexo-convex. There's lots of different naming methods. If I put this on here, the light that hits the top half is going to be bent toward the normal, so bent down when it goes in. And then on the second surface, it's going to be bent away from normal, but that's going to actually make it go down further. The bottom comes in like this. It's going to be bent up, comes out, bent up again. So the light comes through, and if this was a perfect thin lens with the perfect shape, all of these rays would hit at one point. We call the place where they come together the focal point, if it's parallel rays. So the focal point is the point where parallel rays coming into a lens meet. And the distance from the lens to where they meet is called the focal length. So on this, I could label this F is the focal point, and lowercase f is the focal length. Do these rays converge or diverge? They converge. Come together. Converging lenses are lenses that have a convex nature. So this is converging. Now, let's go over and try this lens. This lens is, instead of convex, it's concave on both sides. So concavo-concave, biconcave, double concave. If I put light parallel rays into this, if they come in here, which direction is it going to be deviated? Up or down? Up, because it's going to go toward the normal. And so it's going to deviate away from straight. And so there we see that the light is now diverging. So this is diverging. The light here will not come to a focus. But if you were standing on the output side of this and you looked at those rays, they would look like they came from one point. And so it would look to you like these rays actually came from that point. And so this here is called the focal point for the diverging lens, and this here is the focal length. So you have a focal length for both the converging and the diverging lens. But note where they are. For the converging, I'm going to turn on the light so you can see better what I wrote on the board. Can you guys see what I wrote on the board at all? Okay, good. I was close enough that it was very clear to me, but then as I step back, I'm like, oh, maybe not so much to them. So in the case of converging, the focal length was on the opposite side, or the focal point was on the opposite side from the light source. With our sign convention, if it's on the opposite side from the light source, then it's a positive focal length. So converging lens has a positive focal length. If the focal point is on the same side as the light source, then the light didn't really come to a focus. And so we say this is a virtual focal point, and we have a negative focal length. So this is the basis of our optics. Now we're going to learn a lot more about this in the coming week. I want to get to the eyeball as quickly as possible, but we have to at least have some understanding of what's going on with these lenses. What do they do before we can get to the eyeball? So where to put this? That back on. Put this down. Let's just move ahead here. Here are the different names for different types of lenses. So you should be able to identify these types of lenses. If you look at problem number 4, if you wear eyeglasses, identify the type of vision problem you have and the type of lenses that are in your eyeglasses. So how do you determine? First, the simple test. Is it diverging or converging? That is it convex type or concave type? The easy comparison is measure the center width versus the edge width. If it's thinner in the center, then it's a diverging type. It's a concave type. If it's thicker at the center and narrower at the edge, then it's a converging type or a convex type. So I see we only have 1, 2, 3, 4, 5 people with glasses. You have them with you?
Not with
No.
me,
Yeah. So 6. We have 6 people with glasses with them.
All in a line, too.
On this side, you're right. So check your lenses and see which type they are. And so don't just say it's convex or concave. Use one of these names right here. There are only 2 types that you're going to have, and there's a very, very strong chance that you all have the same type because we almost all have the same vision problem. So we're going to talk about those vision problems and how we correct them. So if you don't have your eyeglasses with you, obviously you can't do that part. You're just left out. Sorry.
So we can't, or 4?
Right, you can't do 4 if you're not wearing glasses. It's okay. It's okay. I won't lower your score. Oh, yes, that reminds me. An important question I was going to ask you. What to do with the pre-lab quiz?
4 out of 4. Is that what 4?
Huh?
I didn't think so.
No,
Yeah, we did it.
I mean, what should I do because we're not doing the actual lab? Okay, I think that's what Ryan was trying to say. Just give everyone a hand. Yeah. So it's,
What are the options?
well, the options would be to not count it at all, or to, well, I don't know. I was going to say extra credit, but it's a little, because I don't like just throwing out extra credit. It makes a mockery of everything we do in the class, right? Yeah, it does. I'm pretty strong on that. Actually, when I was in college, I was taking a class, and there were 2 of us who were doing really well. And the teacher gave us an extra credit assignment, and the 2 of us were like, we got A's. It's the end of the semester, we can't blow it. So we didn't do the extra credit assignment. And he made that extra credit assignment worth so many points that these other yo-yos got higher grades than us.
Yep.
That was not fair. It's probably unfair. Yeah.
I mean, a lot of stuff when you talk about division problems and these questions are like correlates to what that would without.
It does. I mean, it's supposed to. That's
So
the
that's what I'm
goal.
saying, so the quiz is still good as well, because it gets us introduced to the different types of vision problems that we're covering right now in this part.
It is relevant.
Therefore, it's significant.
And therefore significant. So what should I do?
I just counted.
Just count it.
We did, right?
Oh, does anybody not do it? That would want to out themselves?
So,
What happened? I'm right here.
You know.
So should I just count it as normal? Okay. I'm
it applies.
okay. Then I'll do that. That's the easiest thing for me to do. I just want to make sure I. Okay, Ryan just did the official vote. What'd you get?
Yeah.
Okay. Thank you, Ryan. All right. So let's get to.
I'm not sure that one was.
I think I only have 2 more prepared slides, and then everything is going to be off the cuff because that's the kind of time I had preparing this. So when we do our geometrical optics, we do a lot of diagrams, and you're going to learn to do these diagrams. If after I've covered these, you're still confused, look at the tutorials that I have on YouTube for how to do them. There's a lot of different variations. It's not as simple as just two. Yeah.
Is it on your YouTube channel? The one
Yeah.
you can do on it?
It's on the one with the tutorials. So I'm not going to talk about these rays here, but in ray drawing diagrams, because light works the same way forward and backward, we use the definition of the focal point to help us diagram how an image is going to be formed. So remember, it was the focal point when parallel rays meet. If it's not parallel rays. So here I have an example of an object. And we have a convention here to make our lives as easy as possible. When doing ray tracing diagrams, we always put the object so one axis is on the principal axis. Why? Because then its image is going to be on the principal axis and we don't do anything for it. So we only have to find the image of the other side of the object. So the eraser of this pencil is the other side of the object. And then I have three rays. The first ray is going parallel to the principal axis. So this green ray is called the parallel ray. Which I just call it the P ray. So the parallel ray goes parallel to the principal axis from the object to the lens. But what we saw on the screen was that parallel ray is then going to go through the focal point. And so it's going to refract at the lens and go through the focal point. So parallel, then refract through the focal point and keep going. The next ray that I'm going to do is the blue one. The blue one goes through the secondary focal point. So I put an F prime on it to indicate the secondary focal point. It's the focal point on the opposite side of where the parallel rays would come to focus. Right? For the converging lens, parallel rays would come to focus on the right side. So the left side is the secondary one. I made light go through that focal point. Since light works the same forward and backward, if a ray goes through the focal point and hits the lens, it must come out parallel, because a parallel ray would go through the focal point after refracted. And so this ray that's called the focal ray is simply the reverse of the parallel ray. So this is the focal ray, or simply the F ray, that went through the focal point and then comes out parallel to the principal axis. And the final one is the simplest one. This one is called the vertex ray. It's a straight line that goes through the location we call the vertex, where the lens meets the principal axis. And at that point, you have parallel sides, and so it's not deviated at all. And so where all three of those meet, that's where the image is. Just like when we had the focus, all the rays came together. If it's not parallel rays, where they all meet, we call it the image location. And so that's how an image is formed. Now notice in this case, it formed an image that was inverted. It's now upside down because the eraser image is below the axis. The tip is just on the axis directly above or below where the image point was found. So it's inverted, and in this case, it's smaller. If I moved this closer, what's going to happen to that focal ray? Is it going to get steeper or flatter? Steeper. So if it's steeper, it would go like from here to here, and then come out parallel. It would be much taller. So as I bring this closer, my image is going to get magnified. And if I bring it closer than this, then something really weird happens. If my object is here, the ray that goes through the focal point and hits the tip is going to have to go like this. So it's going to come up like this and then come out that way. But of course, the vertex ray is still going to be going like this. So those will never meet, will they? But if I extrapolate back, they'll form an image back here. They didn't really meet. We call it virtual if they didn't really meet. But if you're looking from over there, you would say, oh yes, I see it here. So there's an image, but it's a virtual image. They didn't really meet. With that, we can do the same thing with the diverging lens. In this case, the focal point was on the same side as the object, so the secondary focal point is on the opposite side. And you use the same rules, but the parallel ray comes out as if it came from the focal point. The vertex ray is exactly the same, and the focal ray goes toward the principal or the secondary focal point and then comes out parallel. We'll practice these later. Just getting those introduced. Now we get to the eyeball. So we have four major vision problems that we fix with eyeglasses. The first and by far most common one is myopia, otherwise known as nearsight. If somebody says, Trace, you're so myopic in your thinking, what do they mean? Which means? You're seeing what's going to happen tomorrow, but not the ramifications a month from now. So, an example of myopic thinking. I have a test in physics next week, or 2 weeks from now. I'm going to put all my other classes on the back burner and just study physics. That's looking at the short term. It's going to help you score better on physics, probably. But then you're going to fall behind in all of your other classes, and that's detrimental to you. So in the long term, you harm yourself by trying to do this short-term thing to help yourself with physics. And a lot of people do this. And what you end up is you're perennial behind in all but one of your classes. And you're not getting as much learning as you can. So that's myopic. And Trace, I used you as an example only because I was standing in front of you without knowing. Got to be really careful. Somebody says, my teacher fixed it on. No. Okay, so somebody that's myopic can see things near just fine, but they can't see far things. Now, when we talk about vision, we talk about our near point, the closest point we can focus on, and our far point, the farthest point we can focus on. So the near point, is there an ideal, the closest you can focus on? Okay, how close is ideal? Okay, 25 centimeters is what we use as the standard. But we'd all be happy to see closer. Like, there's nothing wrong with seeing close. So it's not like there's an ideal near point, but there's a standard, and we do call it the ideal. But it's not really ideal, it's just the standard. So the standard near point is 25 centimeters. So I can take this and say, okay, let's see how close I can focus. I see clearly, and I get up, and about here it's starting to get fuzzy. And I'm like, wow, that was only about 20 centimeters. Wow, that's better than standard, right? Sure. But then there's the far point. How far away would we like to focus? There is an ideal here. Infinity, we like to focus on something infinitely far away. So I say, okay, let's see how far away I can focus. And my far point is about a meter. I can focus about a meter. Beyond that, not so well. That's kind of the detriment, because you know who's within a meter of me? No one. So now I can see the front row people pretty well. People in the second row, a little more fuzzy. By the time we get back to Michael, I know he has eyes. I can see the light from the top of his glasses, but I can't see so well. And so I have to have corrective lenses, which I never ever wear. Who's riding with me? So I am myopic. Most people with a vision problem are myopic. And so the problem with people who have myopic vision is their far point is less than infinity. That's the problem. The near point being less than 25, that's not a problem. That's just something that comes along with it. Now, why is this? There's two ways to explain the problem. You have the eyeball, and the eyeball should, oh goodness, should take light. Let me do this on it. Now, I'll do it. You have the eyeball, and the front of the eyeball has the cornea. The cornea is the primary focusing element of the eyeball. Now, I had two students whose parents were both ophthalmologists. And they're like, no, it's not. It's the membrane covering the cornea. And of course they're right. You know, when the light goes from air into that membrane is when it has most of its refraction. But the shape of the cornea is what gives you the shape of that membrane. And so in physics classes, we usually just say the cornea is the primary focusing element. So light comes into that cornea and basically treat the eyeball as if you have index refraction of water. It changes a little bit from piece to piece. So let's say I have parallel rays coming into there. Those parallel rays are then going to be bent toward the normal as they go into the cornea. And if all things are perfect, they will meet back here on the retina. So let's label a few things. Cornea is this right here. And the retina is this here. And that's how I should be for seeing far things. But that's not the only stuff in the eye. You guys have probably almost all taken biology and are about to say, you've got a few important things. So let's fill in. There is that's the iris. Yeah. So the iris, what's the point of the iris? It controls the amount of light coming in. And so it gets bigger and smaller. And those of you who are EMTs have learned one of the things you do, like you have a trauma patient, you cup over their eye so it's dark and you shine light in and you look to see that pupil respond. And with a normal person, the pupil will quickly get smaller when you shine light in. If somebody's had a brain injury, what happens? It does not. They say pupil is blown. It's like the iris is as big as it can get, and it won't change no matter how much light I put in there. That means the brain is not getting the message and responding. What else could cause this to happen? What? It's not a tumor. I'm sure a tumor could, but of course, find a blow on the Another thing that is very common for things not working right when you shine light into the pupil is if somebody is altered. If they are drunk or if they're on drugs, it will do weird and wonderful things. So like you shine light in there and it'll go kind of pulse, right? The brain's not working right. Or another thing that they do, you know, follow my finger and go like this. Leslie's eyes just smoothly went like that. What do you suppose would have happened if she was altered? They tend to go, they can't follow smoothly. Because we have a strong connection between our eyes and our brains. So that iris is controlled by our brains to control how much light gets through. It actually makes a difference to your vision, though. It makes a difference because when that iris is small, what we call the depth of field, the range that appears in focus is very broad. When it's bigger, the range that's in focus is smaller. So in a bright light situation, my vision is pretty darn good. In a low light situation, it's pretty poor. Because in a low light situation, my pupil is large and my depth of field is short. So instead of seeing out to 1 meter plus or minus 500 meters, I see out to 1 meter plus or minus 3 meters. That's the difference it makes with that iris. And we'll talk about why later. What comes between the cornea and the iris? That's not the color I wanted. No, the lens comes after. I remember it as they're in alphabetical order. Aqueous humor, which is essentially water in terms of optics. It's very, very close to the index refraction of water. Then after the iris comes, and somebody said it, the crystalline lens. And you would think the primary focusing element because it's called a lens, but it's not. The index refraction of that lens is not very different from the indices of refraction on either side. On the other side of that lens is the vitreous humor, which once again is almost exactly the same as water. And so there's not much difference in the indices of refraction. Hence, there's not much refraction that occurs. But that lens is very, very important. The lens allows for accommodation. Accommodation is the term we use for you can focus at different positions. If that lens wasn't there, you would be able to focus, but only in one position. But with the lens, you can change the focus. Now, I'm going to quickly go to my last slide here. Presbyopia. I think it's funny. Does anybody know what presbyopia? Oh, perfect. Does anybody know what presbyopia means? Yeah, it's old person vision. Presbyopia is old person vision. Guess what? It's finally starting to happen to me. My siblings, it happened earlier, so I'm still feeling good. Presbyopia is a hardening of that lens. That lens is controlled by sphincter muscles, I believe they are, that will make, I don't know, muscles that will make it change its shape. And so when you relax, it's pretty flat. And then when you strain, when you strain, it becomes more curved and it focuses the light more.
Like squeezing your eye?
No. When you strain, right? Eye strain is not caused by squinting; it's caused by actual muscles in the eye. And so when you're straining, it will make it so it is fatter and causes more bending of the light. So it's an adjustable lens. Well, as people get old, some of us, that lens starts to get hard. So if it gets hard, it's not as deformable, and so you can't accommodate as well. And what happens is you start having your near point move farther and farther and farther out. So that's what presbyopia is. It's a problem with that lens getting hard. And accommodation is the term for us adjusting the focal length so we can focus at different points. Okay, so back to myopia. Myopia is caused when you have the light comes to a focus at the wrong point. The light comes to a focus here. Well, it needs to come to a focus on the retina for me to have a clear vision. So if it comes to a focus closer than the retina, I don't see clearly. Now, if I bring something closer, it will move the image position farther back. And so if I bring it closer, then I can focus on it. So the problem with myopia is either eyeball is too long or cornea is too curved. The cornea is doing too much focusing. So those of us, well, let's not go with those of us. Let's simulate this and see how we correct it. So, here's my eyeball. And I have lenses here for correct vision, nearsighted, farsighted, and the corrections. So I don't know which one's which offhand. So I'm just going to randomly put number 1 here. Would you call that good vision or a problem? Good vision, why? Came to focus on the retina. Bueno. So number 1 is good vision. Number 2. Ruh-roh. This person is nearsighted or myopic. So what do they need to do? They need to have less focusing. Well, how do you do that? How you do that is you put a lens in front that is going to spread the light out. Which kind of lens will spread it out? Converging or diverging? So I put a diverging lens here, and now it is coming to a focus here. It's just you can't really see the lines. They faded out. There. So with the diverging lens here in front, we were able to push back the distance where it came to focus. Now all is good. So if you have eyeglasses that are diverging in nature, that is, that are thinner in the center, concave nature, then that means that you're correcting for myopia. I'm going to stick with this. Our last kind of vision problem is hyperopia. Hyperopia comes to focus out here. Again, that's a problem. So what do we need now? We need a converging lens to bring them to a focus at the back of the retina. So if your glasses are thicker in the center, then you have hyperopia. So we can see how we do corrections. Our last thing to understand then is to be able to calculate these. So once again, into the mix. How we correct this is first we identify, now the problem here, which one was the problem? Was it the far point or the near point that's the problem for somebody that's myopic? The problem is the far point. But the one we actually use, actually that's the one we're going to use then to correct is the far point. So we're going to do something to correct that far point. So we want to take or use a lens that moves image position to the retina when object at infinity. That's what we want to do. And now the question is, how do we achieve that goal? So I start by saying, okay, here's my eyeball. I'm going to measure my far point. So step 1. Measure far point. This is something that each one of you needs to do. So let's go ahead and just do that right now. You might need to have a friend work with you if your arm's not a meter long, which none of us are, and if your far point's that far. If your far point turns out to be larger than a meter, just use 1 meter for your calculations. So everybody, grab a meter stick, measure your far point. Just choose an eye. Yeah, it could vary from eye to eye, so just choose an eye.
So, letter eye or worst eye? Worst eye or letter eye?
Choose your worst side. It's more interesting. Bring the meter stick up to the outside part of your eye, so it's pretty much at the same level as your eyeball. And make sure you have the metric side where you can read.
Can you do it without our glasses?
Yeah, do it without your glasses, definitely. You just move back until it starts to appear fuzzy. Okay, so inside. So put things there. And then 10, 30, 42.
Oh, wow.
We'll have purple. So write that down.
Yeah, cool, that was
I
my
think it's Mr.
So put
I don't think I understand.
So how clear is clear?
How clear is clear?
I don't know.
How dark is dark? How bright is bright?
You're right.
How shiny is shiny? That's one of the great well, I had a program who worked last night. When did short?
Well, no, she had to have both.
You're at like 30.
Blurry right here, so that's right.
You're looking at how far away.
Do it again.
So when it starts getting
Yeah, you're like
that's the same.
From 6'1".
When you go to that conference, this is essentially what they're doing, except for they're doing comparison instead of.
I'm gonna try to just try to.
Wow, I'm so blind, I don't wanna do this.
Yeah.
So I'm wearing contacts. That's the way
Yeah, and then he came over to us about it takes words so he can pass it in. And I'm like, stop passing. He said anything about competition.
Oh,
Wait.
Wait.
Well, I don't know what it is. Because usually they tell you that you are going to
I should do glasses. I only did my contacts. Because I figured if I'm gonna buy something, I'm gonna buy contacts.
Not too much.
Stick with current glasses.
Yeah.
You guys don't know.
Mine was
I'm wearing contacts.
I wouldn't say that.
Yeah.
Yeah, well, yeah.
Yep.
But you know my contact lens power.
I'm waiting for
It's a perfect.
Maybe I can
I
just
mean,
use the
like
reverse.
here.
You could, but it's fine, you should one.
It's made me recognize.
Yeah.
It's like,
It's nice to see, right?
no, but I showed my.
I'm gonna say that.
Yeah, that's what I'm saying, though. I showed my friends that, right, they were doing the same thing. They're like, remind us not to drive in my cars. And I'm like, no, it's just.
Here's the thing, can you see a skunk through that wall?
One convex, one
But I can smell
I
it.
don't really know what.
I've never gone to a red.
convex,
I've never, honestly, though, I feel like it's usually the other person on it. I don't. You did what?
I gotta go with.
Yes, sir.
Can we based on our ability if we can still hear? This is perfect focus meaning we can still hear
Your
Okay, let's ask another one. What type of contact, how long has it been?
What type of contacts and how long did you see it?
Like daily, monthly, okay, so this is monthly, how long would you do?
I think I can see.
If you
How
see
much time?
a day, you had a month, you only had it in here a day. Did it dry it out? So the wind took your business. The wind took your business. So I've had my contacts.
Your pen looks good.
Like,
What was that?
Not horribly blurry, not horribly.
Oh, the name.
I can, oh my god.
I'll just go ahead, scroll back to the picture.
I can see it being blurry. That's
It's okay.
And like I said, there are different names some people use. See, so another name you could have used is concave meniscus.
You said that people
So
That sounds
people,
like a
no,
wreck.
no,
That sounds like a right.
I'm talking about me just going straight and someone decided to sorry. It's not my fault, that's fine.
I don't know, please do the tango.
No! It's my fault. I've never read, so.
It's mostly your fault. Like if you're tangoing
Okay.
something your foot, is it mostly your fault?
Oh, still not done.
So if someone is drum driving and they just decide they want to get even to take.
You had to do that again.
Okay, wait. I do like the Leslie's, they also decided they want to.
sure what the road is. You guys are probably not do it.
I'm gonna do it.
Yeah, that's what I'm saying.
I'm not saying you have most of the blame, but I'm just saying you're not
No,
100.
no, I hate that law.
Okay, so everybody's done it now. Let's go to step B. Or step 2, not B. So step 2. Find lens power. And I have to describe what lens power means, but it's simple. That will make an image at far point if it. Because the problem is the far point, that's why we're taking the ideal far point of infinity, and then we're going to make a lens that puts an image where you can focus on. So, doing this pictorially, I have my eyeball, and here's the physicist's eyeball. And then I'm going to place a lens. Okay, my lens is going to look like there's my lens. And then I'm going to have an object out here. And it's going to make an image at the far point. Do you understand our goal here? Now, the light from the object is coming like this, right? If it's going to make an image back here, which kind of image is it making? It's a virtual image, right? Because the rays didn't really meet there. But to the eyeball, it looked like the rays actually met there. So it's going to make a virtual image on the same side as the object. And so the question is, which kind of lens are we going to need? Now, I'm not going to answer the question. I'm going to let the math tell me. So for the math, I swear I'd written the equation here. Okay, I wrote it here. The relationship to allow us to calculate this is 1 over the focal length is equal to 1 over the distance object plus 1 over the distance image. This is called the thin lens equation. It's also called the mirror equation. It works for both. So we're going to have here distance object. How far is it from the object to the lens? Infinity. Distance object is infinity. Distance image, oh good sir.
1 meter.
For your problem, it's 1 meter because your problem is a contact lens. Why does it have the name contact lens? Because it's making contact with the cornea. So the far point distance is the image distance. But one more thing. That image distance is on the wrong side of the stinking lens. If the light goes through and it forms an image, it's going to be a positive image distance. But if the image is on the same side as the object, it's going to be a negative image distance. So you're going to have your image distance is, so for your case, for my case, I'm doing a different one. For your case, the distance image is equal to minus the far point. Because you're doing a contact lens. In my case, I'm going to do eyeglasses. A simple standard is that your eyeglasses are about 2 centimeters in front of your eyeball. If the eyeglasses are 2 centimeters in front of the eyeball, then my distance image is going to be that 2 centimeters minus the far point. So for contact lenses, it's 0 minus the far point. For eyeglasses, typically 2 centimeters minus the far point. You'll see some homework problems where it says they're 1.5 centimeters in front, well then it'd be 1.5 centimeters minus the far point. So now we put those into our thin lens equation. So putting those into the thin lens equation, And I want each one of you to do your own calculation. Let me start with what units should you use? What do you think? Go ahead, say it, Wes. Oh, I saw him go like this, and I thought he was saying, what does it matter? As long as you're consistent, it shouldn't matter. But if you are the optometrist, you use meters. So do your calculation in meters because we want to be able to compare with what the optometrist gives you. Yes. You're solving for the focal length. Actually, let me give you why the optometrist uses meters. The definition of lens power is 1 over focal length in units of inverse meters, and they call them diopters. So 1 diopter is equal to 1 over a meter. And so that's why the optometrist uses meters, because they give you power in diopters. Yeah. Well, what is 1 over infinity? 0.
Oh.
Okay.
I gave you the easy one because it's 0 for the 1 over distance object. So your prescription is 1 diopter. Is it a +1 or a -1 diopter? -1 diopter is correct, sir. That minus means that you need a diverging lens. You need a lens with a focal length of, since it's 1, it's going to be 1 over -1, so still 1, -1 meter. Yes, Michael?
So bars is going to be 0.
Yeah, unless you have magnitude. Did I get it, contact? You don't know what you call me? Yo, that kid had many glasses though. You just like pop me in place and then cover it.
That looks so weird. You see people walking around with
You never already left.
Okay, so those of you who aren't wearing contact lenses, what kind of prescriptions did you calculate in today's lab? You just calculated a prescription for your contact lenses. What did you get? I know what you got, Ryan. We already talked it through. Well, you just have good vision. Yours is, of course, just a calculation. So, anyone? Yeah, Mira can tell us what hers really would have been if she wasn't wearing contacts.
Yeah.
Okay, Okay, negative 3.38. Okay, so now you wear eyeglasses. You also wear contacts. Okay, so what is your contact? Negative 4. Okay, so negative 4 would have been 0.25 for your far point. And your far point that you measured was what? 0.28? 0.29. So you were off by about 4 centimeters compared to the accurate measurement. Right, when you go to the optometrist, they're a lot more accurate than you just roll your finger down here saying, clear, clear, fuzzy, right there. And so that's why you're off, but you're not far off in terms of the measurement. It does seem far off in terms of the number. That's why they need to be very careful with the optometrists, right?
I think sometimes too, I've noticed that they tend to overcorrect you a little bit. If it seems a little bit clearer, you don't want to use your eye.
Yeah.
Well, like I have a stronger prescription of contacts for glasses because I just like astigmatism of counteracting it. So it's just
Well, let's compare what you would have. Let's take Lydia's numbers. You said it was 0.29?
Yeah, 0.295.
Well,
I'm adding.
given our uncertainty, I'm just going with, well, I'll take your 0.295. So taking Lydia's numbers for her contacts, okay, I'm going to add another page right here because I wrote on the next page already. Oops. So for Lydia, far point equals 0.295 meters. And so the power for contact is equal to 1 over infinity minus 1 over 0.295 meters equals, and what number did you say that gave you? And actually, I'm going to put a plus here and then minus down there. Minus 3.39. Minus 3.39 diopters. So that's what it would be for contact lenses. Now, if Lydia instead is wearing eyeglasses, it's still 1 over infinity because what's 2 centimeters compared to infinity? Plus 1 over 0.02 meters minus 0.295 meters. And so here we have to do a different calculation. And where's the button? There it is. And so that gives us minus 3.64 diopters. So the power is going to go up when you change to the contact or to the eyeglasses because of the difference in the offset. Now, you said yours was the opposite direction because of the astigmatism problem, right? But the prescription is going to be different for eyeglasses compared to contacts because of the different position of the lens. Lydia.
Astigmatism necessarily change the power there. Let's get super
The answers depends on how you look at it, right? So there's no clear definitive answer. Astigmatism is, well, we already covered presbyopia, so let's go to the one that has astigmatism. Astigmatism is caused by having a cornea that's not symmetric. If you have like more curvature in this direction and less curvature in this direction, what that means is you're going to have light that is coming along this axis has a different focal length than light on this axis, which means you can't focus perfectly. No matter what you do, you're going to have some of the lights out of focus. So they test this by just doing that grid where you have a bunch of lines in different orientations, and they ask you, which line is darkest? Everybody knows all the lines are the same darkness, right? I mean, you take the book and you rotate it because you want to know for sure, and it seems to stay in the same place. That's because if you're focusing clearly, then it's going to be narrower looking. If you're not focusing clearly, it's going to look lighter because it's fuzzy. And so that tells them what the axis is for your astigmatism. And then they carefully measure what your focal length is, or focal distance is for things in one direction and things in the other. So that first test is to find the axis, and then they do careful measurements to find the difference. And so you have two different powers. And so the lens then has to be ground so it's not symmetric. So you have two different powers to correct for each direction, which means the orientation of that lens is real important. If you take your eyeglasses, you have astigmatism, and you rotate them like by 45 degrees, it's going to mess stuff up. For that reason, you used to not be able to get contact lenses for astigmatism because the contacts would just move around. But these days, at least if I understand it correctly, they weight the contact lenses. So you put it in, and it will rotate so this side's down. Of course, if you stand on your hands, it's not going to be good. But you know, the contacts then allow you to correct for astigmatism these days. One more thing before we talk about our last vision problem. Myopia. what if I don't want to wear eyeglasses, and I don't want to wear contact lenses, and I want to see clearly? What if I have all three of these issues? What can I do? I can have a laser eye surgery. Now, back when I was in graduate school, you could have eye surgery, but it didn't involve lasers. What they did is they would take you in, after very carefully measuring what your problem is, they cut a little circular flap and take back the cover of your cornea. They still do that today, don't get all upset yet. The barbarian part. They're like, we need to change the curvature of that cornea. So how are we going to do that? Well, you know, if I get cut, see my chainsaw cut here. I got scar tissue that grows up. So maybe if we just kind of mangle that cornea, it'll form scar tissue and it'll have a different shape. And so based on average scarring of the cornea, they carefully calculate, okay, I'm going to make some slices in the cornea, and then I'm going to put the cover back on and send you home. And over the next couple of days, your cornea is going to heal. Your eyes are really good at healing. And that scar tissue is going to make it have a different shape. And if they did their calculation right, maybe you'll see better. And so they wouldn't guarantee anything better than 20/40 vision, because your different people scar differently. Pretty barbaric, right? Well, then they do the stuff that I got my PhD in. I got my PhD in vaporizing transparent materials using a laser, which is kind of tough because if it's transparent, the light shouldn't be absorbed. And so they take the same type of lasers that I was studying, and they very carefully determine what shape the cornea will need to be. And then they have a little grid, and the computer controls, and they take that flap off again. And then they have the computer aiming the laser and goes zap, 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 zap. And it vaporizes, we call this ablation. It vaporizes parts of the cornea to reshape it. And in the early days of this, they would only do myopia because you thin the center to reshape it to make it so it's going to extend the focal length. These days, they will also do it for hyperopia to some degree. With hyperopia, you need to thin the edges to make it so it's more curved, and there's more concern because you could then weaken the cornea on the edges so that it could tear. So that's what photorefractive surgery is. Photoreactive keratotomy, I think is the name for it, PRK, is using a laser to reshape the cornea. And a beauty here is you have very little scarring that occurs, so they can very accurately reshape it, so you can get much better vision with the laser surgery than you could with the slicing barbaric method. And you go home with the corrected vision. So when you do it, they give you eye drops to make your corneas. Yes. To make your irises enlarged. And so your vision is going to be a little wonky until that eye drop wears off, but the next morning it should be fine. And so it's reasonably good. One of my friends was an airline pilot, and their industry trade magazine said, do not have this done if you want to be an airline pilot. Because one of the side effects that you can get from the PRK is that you're essentially making a grid pattern on your eye, and you can start to have kind of a rainbow halo effect thing that you see in your vision. And that will flunk your vision test for the pilot, and you can't be a commercial pilot anymore. So they were, at least back then, this was 20 years ago, telling pilots, don't do this. There are pilots who have lost their license because they had this surgery because they didn't want to wear eyeglasses. Okay, we only have one more thing to cover. We've done everything on this already, right? So the last thing to cover is the less likely of our vision problems, hyperopia. My younger sister had hyperopia. Hyperopia is a problem where you can't see near things. You can see far things just fine. And so it's also called farsightedness. And so this is a problem with the near point. Now, once again, if we think about the eyeball, the problem with the nearsighted person, the myopic person, was that the eyeball was too long or the cornea was too curved. This problem is going to be the eyeball is too short or the cornea is too flat. Now, I talked about the rareness of this. Typically, as you age, I mean, they say your eyeball stays the same throughout life, but my experience says apparently as you age, your eyeball gets a little bit longer over time. And so we tend to move into nearsightedness as we age. Now that's different from presbyopia. Presbyopia is much more pronounced and is differentiable from myopia in that with myopia, your near point moves. Okay, I said it wrong. Hyperopia is differentiable from presbyopia because with farsighted or hyperopia, you're going to have your far point and near point move together. But if you're presbyopic, your far point stays the same, and it's just your near point that changes. So you can differentiate between the two. And it's possible to be both hyperopic and myopic. Hyperopic, you can't see near things because that crystalline lens is hardened. I think that's it, right? Presbyopic, you can't see near things because the crystalline lens is hardened. Myopic, you can't see far things because your eyeball is too long and the cornea is too curved. What happens if you have both of those? Yeah, your range of vision is pretty limited. And so that's why Ben Franklin invented the bifocals, so that you could have two different places that the glass is correct for, one for reading and one for looking at distance. And then people said, Ben didn't go far enough. We should make trifocals. So you have three lenses, one for close, one for intermediate, one for far. And now these days, you just get a graded lens. So if you look like this, you'll be focusing on close stuff, and as you move it down, you're farther away. So with those lenses now, the continuous gradient, you just adjust your head tilt and you adjust how far away you're focusing. And those are only necessary for people who have both farsightedness, or excuse me, nearsightedness and presbyopia. Yeah, pretty much, yeah. Yeah? No, I just said nearsighted, or yeah, nearsighted and presbyopic to make sure I wouldn't make a mistake. No, hyperopia at first doesn't appear differently from presbyopia, except for, notice this has the far point greater than infinity, whereas presbyopia far point stays at infinity. Or if you were nearsighted, far point stays shorter than infinity. So hyperopia, the correction is going to be pretty much the opposite. So for correction of hyperopia, step one, measure the near point. Why? Because hyperopia is a near point problem. You can't focus on near things. You can focus on far just fine. So you measure the near point, and then step two, calculate lens that will take object at ideal. Okay, what does ideal mean? I'm going to put standard here just so we don't get it confused with that's what we wish we had. Standard near point, which is 25 centimeters, and create image at actual near point. So I'm going to draw a picture for this and we'll do a calculation again. Here's the eyeball. Here is the near point standard. And here's the near point actual. And again, I'm going to put a lens, and I'm going to say this is 2 centimeters again. So remember with our calculation, if it's 1.5 centimeters, you replace the 2 with 1.5. And now I need my lens to take my object and make the image as shown. So my object distance didn't have space. My object distance is this distance here, which would be equal to the near point standard minus 2 centimeters. 2 centimeters being the offset from the eyeball to the lens. So that's my object distance. And then my image distance is equal to 2 centimeters minus the near point actual. So let's take a situation. Let's say somebody has a near point of 40 centimeters. 40 centimeters, that's like this far away. We'd really like to be able to read something closer than that. And so we're going to correct it to 25 centimeters. So for an example, distance object then is going to be equal to 25 centimeters minus 2 centimeters equals 23 centimeters. And distance image is 2 centimeters minus 40 centimeters equals minus 38 centimeters. So the power is 1 over the focal length is 1 over distance object plus 1 over distance image equals 1 over my distance object of 0.23 meters plus 1 over 0.38 meters. Oh, so much harder because you have to calculate 2 numbers instead of 1. I forgot a minus sign. So that'd be 1.72 diopters. It's a positive number now. That means it's a positive focal length. This focal length is 1 over power. And so this is going to be a converging type lens to correct hyperopia. So that's our vision correction. You can see there's a lot of physics in this vision correction for these basic standard things. If it's something we didn't mention today, there's probably not a physics solution, but something else necessary to correct it. So any questions about the physics of the eye that we've learned today? No? You understand it well? Okay, I see some heads nodding. That's always a good thing to see people who actually, yeah, I think I understand that. All right, have a great day. We're out of lab 45 minutes early.
So is this what you wanted me to calculate for this one? I don't know if I did this. Is that last?